Hi. Hi, myself Jitendra. I've been with AWS for like 5 years, and I'm working as a senior lead consultant in AWS professional services. Thank you for joining our session.
Thank you. So we'll talk about generative AI. It's a buzzing word around us. And then we'll cover the role of vector in generative AI. We'll talk about the Postgres extension pgvector. Then we'll cover some of the advanced topic on optimizing the search using the pgvector index IVF flat and HNSW. Then we'll talk about some of the best practices for using pgvector, followed by a demo of a short demo of application, and then we are open for Q&A. So we all know it's a buzzing word. So what is generative AI? Generative AI basically is a category of AI algorithm which can generate new contents out of the trained data. So, and what this new content could be? This new content could be anything. It could be an image which you might have not seen earlier. It could be a code. It can generate code for you. There are applications which using which you can generate codes. So it could be even for it can be used for the chatbots and virtual chatbots with communicating in the natural language with us. So it's all around us now. So what are the generative AI being powered by? It's basically powered by the foundational model. So these foundational model are basically trained on a large internet scale, vast amount of generalized text of data. But before the foundational model, the norm was to build the AI model on a domain-specific task and on a labeled text of large amount of data. And this approach was very cumbersome, and it was CPU intensive, and then it was highly dependent on the labeled text of data. The developer has to bring the data and then label it and then create a model out of it. But with foundational model, since it is trained on a generalized data, you can use this foundational model to create generalized generative AI application to create generalized content with remarkable accuracy, like image generation. You can have a chatbot which can talk to you in a natural language of your choice. So that is the power of the foundational model. And on top of the generalized data, you can further fine-tune your model with additional data, and then you can use for your domain-specific application, so that you can leverage the ready-to-use pre-built model, and then you can further fine-tune it and adapt it to your business use case and build your own application. And these foundational models are basically a set of neural networks which are trained on billions and trillions of parameters. So now we understand that it's all the base at the core, the foundational model is there. But, and if we try to understand the concept in more detail, let's, from here onward, we'll try to talk in terms of LLM, which is the specialized foundational model majorly dealing in text and natural language processing. So for an LLM, how will LLM understand the actual meaning of the word and the context between the words? So to understand that, we must understand a term called embedding. So these embeddings are basically nothing but the numerical representation of your object. The object could be a natural element. This could be a word, phrase, a document for that matter. So you bring your product information or your business contextual information, you chunk your data into multiple chunks, whatever is the contextual meaning of that, and then you pass that data to embedding model, which will create the embedding out of that data. So now we have my data in the form of embedding, and now the question is, where will I store this data, which is the embedding, the numerical representation of my data? The answer to that is vector. So vector is the same thing that we have studied in our class 12 while we were doing our while we are understanding the velocity, acceleration or displacement. So velocity being the rate of change of object with respect to time. So again, it has two dimensions, rate of change of object and time. So as we know, vector can have magnitude and direction. It has two-dimensional property to it. But in LLMs, in case of LLMs, in large language model, a word can have multiple dimensions. It could range into tens and thousands of dimensions to it. And these dimensions are basically adding property and characteristic to the word. So for example, in this case, let's say I have a word called flight. I've given an arbitrary number as 0.2, 0.1, and 0.3 as a vector number. So just to understand how a word will look like in the embedding world. And if I take this data, like all my words, embedding words, and I put it into a 2D graph, let's say, just to explain, like it's a three-dimensional, but to make it more clear, it's a 2D graph where I plotted the distance of the vector points here. Now, LLM understand that your word is there in the form of embedding. How will LLM understand whether what word is closely related to what word, and what is the contextual meaning of the word? So there is something called as vector similarity search. This similarity search is basically calculating the vector distance between the two vector points. Now, flight and airport keywords are more closely related to the context, and that is the reason they are more similar. And whereas the flight and milk word is little far away and it is less similar in the context. So that's how the LLM is basically calculating the distance, vector distance, to understand the semantical meaning of the word, and then it will come up with the correct answer for you. So what this distance could be? So majorly there are distance like, these are the most frequently used distance that we have is Euclidean distance, cosine, and dot product. Euclidean being the, it's a 2-point straight line distance between the two vector points. So it does not take care about the orientation of the vector or the angular property of the vector point. It is mostly recommended for product recommendation system. And whereas the cosine is the orientation of the vector, it does not cater to the magnitude of the vector. It is mostly related to the orientation of the vector, and it's mostly used in semantic search and document classification. So depending on the use case, you can use you can make a choice of your similarity distance that you are choosing, that you want to choose according to your use case. And we have a dot product, which is basically the overlap of cosine and Euclidean, which is basically the measure of the magnitude of the vector and the angle between them, and is mostly used in collaborative filtering and recommendation system. So now, although LLMs are powerful, but LLMs are not up to date, do not have up to date information. For example, if I ask LLM what is the weather condition in Bangalore today, it might not be able to answer that. It will say, I have data up till this point and I don't know about that, or maybe it say I don't know. And similarly, the LLMs will not have data with respect to your org specific data. Let's say my data, my business data is sitting in my database, and that data is confined to my org only. It is not available for LLM. So LLM will not be able to answer questions like what is the, let's say, what is the price of flight between JFK and Atlanta. It will not be able to answer that, because that contextual or the business specific data is missing from the LLM. So there is something called as retrieval augmented generation. There's a technique with which we enable the LLM to answer that question, and with this we provide that knowledge base or the product specific information or my org specific information to LLM to come up with the right answer. So now LLM is able to answer that question correctly in terms of the right number. So to put the picture, entire picture, how a general generative AI application which is using RAG will look like. So let's say I have a document data, I have some data with me, and then I broke that data into document chunks, and then I pass that data into embedding model. So now I've created the embedding out of my data. I have to store that embedding somewhere. I'll store it in some database. Now once my embedding is stored, let's say I have a generative AI application, and where a user asks such kind of question, that question again is passed through embedding model, same embedding model. And it will again generate the embedding out of that question. Now this question embedding is again searched for similarity search in my database. This is where my distance operation will come into play, where it will check the Euclidean distance and it will find out the closest distance for that question vector. Now, finding the closest distance for that question vector, it will come up with the context and the question vector. Then that is searched through LLM to generate the response out of that LLM. So this is how the complete picture will look like when we are using any of the generative AI application.
Can you go back to the previous slide? Hey, by this time, I believe we got a fair idea how the LLM is working out, right? So LLM is nothing like you study for a year and given the exam, right? But what you study, you can only answer to those questions. This is how the LLM works. And if you give you, like we are all mature, we have done our graduation maybe and a lot of other thing, right? If there is an opportunity, if somebody give us the open book, we might able to, give answer or find answers from that book and write it down, right? We can do that one. So this is how it is happening. So what we are trying to do is we have created the index of the, and how you read the book basically. If you're really looking for a particular word or particular subject, you definitely go to the index and search for the page number, go there and read and find out the answers. This is how it's happening. So this is how this whole RAG thing is working, and this is how the LLM is getting famous again more and more in various areas. So now thing is, it comes with certain challenges. Let's shift our gear to a little more technical and deep dive on the various stuff here. Time to generate embedding, right? So I have a huge amount of data out there. I need, why I'm doing the embedding, why we creating the vector, so that we can search in them. So creating the embedding is a time-consuming task, right? And now it's millions of vector we have to generate. We have a lot of data, and embedding has to be generated first. Then we're going to search, similarity search, and then place them to the in context and ask question to the LLM so that it can answer. Now, it's time to generate embedding. So what's the size, right? It will come in, we are a DBA, we are the database professionals, right? Maybe we definitely consider what would be the size to store these embeddings. So here, in our example, we are taking like Amazon Titan embedding, which generate 1,536 dimensions, right? It's a big. And 4-byte float number, which turned out to be 6 KB per embedding. Is massive. So if you have to store millions of embedding, it's going to take 6 gig almost. It's a big thing, right? So we might think about, why don't we compress it? Can we compress random floating numbers? I believe as of now, there is hardly any algorithm which can really give us a huge or good amount of compression ratio. So the compression is not possible as of now, right? Now, we have created the embedding. We have our indexes. Now we have to query and find out what are the similar vector out there or similar embedding out there. So vector comparison, vector to vector comparison, we can do it. This is called the distance operation. For distance operation, we have to compare each vector against the rest of the other so that we can find out the right difference or right distance between them so that the shorter distance or shortest or closest one, right? We can find this out. So it's massive operation. It's with millions of embeddings, millions of data, right? Comparing all of them together is massive work or computational work, right? So definitely we think about how we can make it faster. Can we make it faster? Yes, we can make it faster. There are ways which we're going to talk about now. So vector comparison, we have to compare each dimension in each vector. That's how we can do it. But to shortcut our faster comparison, we can compare less vector, but still we have to compare all the dimensions. Now see how we can do it. And that's when we are not comparing all the vectors means we are approximating something. Maybe these many things are very close to each other. And this is called the approximate nearest neighbor. Finding the similar vectors or similar words without comparing all of the vectors, which will be faster because I have less data to compare. I have less work to do it, so I can do it, right? Now, when this happens, we are not comparing all of them, and it's approximate. It gives a really new term for us is recall percentage. So let's see what is the recall percentage here. Recall percentage is relevancy. It's about how accurate my data could be. For example, suppose in my database I store 10 similar vectors, and I run a query, it returns me only 8 vectors. There are 10 out there, but I got 8. It means I got the 80% accuracy. If we need 100% accuracy, we need to compare all of them. Otherwise, there's no possibility, right? So we have to really consider about it and see. It might be good, or it might be, it depends on the application. It works for us, maybe certain application where some results are okay or similar results are okay. Somewhere we need 100% accuracy, then we have to think about something else, right? And we will, in the coming slide, we'll be talking about how these things are implemented, how these things are so accurate and we can rely on them, right?
So now we know that we have already, so this could be the best operational relationship data out there, database out there to have a choice on. And so these are the various features that we have already know, and we don't have to stress upon that. So major point that I would like to stress here is that on the highly extensible part of the, so Postgres is basically architected to be highly extensible in nature. You can bring any of the extensions out there and bring that functionality into Postgres. You just need to install that extension, and then you can bring that functionality. That is the major advantage using a Postgres. And the other advantage that you can have is it's an operationally efficient, because let's say if you're already using a Postgres DB in your application, then why not bring your embedding data or your vector data into Postgres itself? So that you're make it more operational, efficient. So that's where the Postgres pgvector extension come into picture. And this is the extension which is open source and is being supported Postgres version 12 onwards. And it basically adds supports to store your vector data type in your database. And then it also gives you various indexing methodologies like IVF, flat, and HNSW, which we'll discuss in the later slides in detail. Then it also gives you the approximate near neighbor search and the KNN, which Jiten just now explained, that it will be approximate near neighbor option. It will give you to check only the approximate near similar vectors. And then, as I said, you can co-locate your normal RDBMS data along with your vector data. So that is what the Postgres offer. Like you can put your normal, let's say you have an application which you're using on Postgres, and then you can, and if you want to add your generative AI use case, you can bring in your vector data and then store it here. And it also gives you the distance operator that we have spoken about, Euclidean, your cosine, and dot product. And this is a small example where basically I'm showing how we can create an extension, vector extension, and then how you can create a small table. And then I'm just creating a small table with 3-dimensional vector just to showcase how the operations and the data will look like. So in this example, I have taken 3 words and then arbitrary 3 vector numbers here, so that to understand how the distance of these numbers or the vectors will look like when we'll use in our database. So it's a very small example where we are using only 3 vector points, but in real world, in LLMs, the dimensionality will grow across thousands and 10,000s. So that's where the distance operation is very heavy operation, as we have seen. So here, in this example, we can very clearly see that we are calculating Euclidean distance between the flight vector and the airport vector, and the distance is coming out very less, it's 0.28, whereas the vector distance between the flight and the airport is far apart. So that's how the LLM understands that these 2 words are contextually closer to each other, and the other words are not that similar. So that brings us to the topic on the HNSW, the index of the offered by pgvector.
So as we talk about in the previous slide, that we have to compare vector with all the vector, and it's taking time consuming. So what we do to improve or optimize the query, right? We write a simplest query possibly, or we cut down the selected data, and we create indexes, right? So indexes are very, very important here. And to implement the approximate near neighbor search, pgvector allow us to create 2 types of indexes, HNSW, which is hierarchical navigable small words. And the other one is IVF flat, inverted file, flat file. So let me walk you through the, please raise your hand in case I'm going very fast, or we are going very fast. I'm happy to help you out, or otherwise, if time doesn't allow, we'll do it in the booth as well. So hierarchical navigable small word, the HNSW, is a multi-layer graph-based index. It will create multiple layers. In the top layer, we have less amount of vectors. And as we go down, we have denser and denser vectors. And each vector pointing to other vector which is similar to it. Right? So each vector knows who are the other similar vector to him. So this is how, when we try to search, when we run a query, it starts from a top point. It finds there is a vector which is a little closer to him. And then it finds out the shortest path, because each node is connected along with them. They know these are my nearest vector. It finds out which is the shortest distance to reach to the point. And it travels through the nearest one, and then the shortest one, and the other one. And in the bottom, we have the data where we resided. And this thing happens at the index building time itself. It's not about the query time. When we create the index, this whole thing been done. The tree is there. All we have to search now. So there are, while creating the index, this index, we really need to consider two important parameters. Most likely the default will work, but let me walk you through why, how we can configure and what's the importance of that. We talked about recall percentage, right? So here, consider the recall percentage and the query performance. These two things go together. M stand for the node or the vector will have so many pointers or link to the other vectors, so that it can point 16. By default, it's 16. And while doing this operation, by linking the vector to the other vectors, it will maintain a queue of M construction. This is the M construction which is going to be used to define how big length could be, how much queue need to be. The bigger the queue is more closer to, or it will have more accuracy, but it will create more memory, it will create more computation, so it will take more time. Similarly, while querying, we can again define a EF search parameter, which will define, while searching the data, or while searching the similarity search, how many vector I should keep in the queue to compare and find out who are my nearest one. So bigger the queue again, bigger the queue, more comparison, but majority of work already been done at the time of index building, and then at the query time, we can still tune a little bit more to make more similarity search more accurate. And this is, you have to experiment sometime with these parameters, but most likely, most of the application, these settings works fine. Now, let me go to the IBF flat. This is a cluster-based index. This is, again, support the approximate neighbor search, and it's cluster-based. So what it does is, it divide, or it create multiple cluster or multiple list of similar vectors. And it set the centroid in between, so that when the search query comes, it first go search for the centroid, who are nearer to him, and then it search within that cluster only. So see, if suppose we have 100 people out here, maybe I can categorize in 4 or 3 groups, and maybe one group is for Postgres, one group is for MySQL, another one for DB2. Now I'm looking for people who are expert in Postgres. I wouldn't go there DB2 and MySQL. I simply check the cluster for Postgres, right? This is how it works. And now there is also some parameter that we have to consider. As we talked about the list or cluster, the first parameter is list. List is how many clusters I should be having it. The best practices say, if we have less than million rows, simply divide by 1,000 and have it. That many cluster or less should be enough. If more than that, simply square root of the number of rows out there. And now, probe, the other important parameter. So first parameter list is about when we're creating the index. When we query the data, we need to consider about the probe. Probe means how many lists I should be looking before returning the results. Maybe MySQL group might have some Postgres knowledge as well, right? I might like to see here and there, so I might get more data and more relevancy. All right? And PGVector also supports parallel build, which is faster to build the index. This is very important because first time while you're building it, it's going to take time, some time. There is a small difference here about what's the main difference between here. I'll talk about only two. Uh, Definitely the build time is faster in IVF flat. Graph is more, it will take more time to create, but it's more faster to retrieve as compared to IVF flat. And remember one thing, recall versus performance. The HNSW is very efficient because it's going by the hierarchical structure and it's having better recall percentage and performance. IVF flat on the other side might be a little lagging, but it's still okay. And while building, definitely the memory needs, the memory requirement for a cluster index, the IVF flat is small, but definitely the bigger the tree, bigger the memory it would need. And one more very important thing is, IVF flat, you have to create when you have populated your data. Before that, it won't work. And if you change data, you might need to consider, if you have massive change in data, you might need to consider to rebuild it. Where IVF HNSW, you can create on the empty table as the data grows. It will create the tree and graph, but it will impact on your insert or update. So if you have very huge transaction system, I wouldn't recommend it, but you have to consider the use cases where you're gonna adopt to it. Here are some of the design patterns that we're talking about. So while choosing the index type, we have to consider what sort of embedding model we have chosen. Because each embedding model is trained with certain distance function. So the index should support that. Otherwise, it might give you the little random results. Pre-filtering, I believe everybody knows about it, pre-filtering, no? Filter the data as much as you can so that my comparison become lesser. Read less from the disk or RAM, and then you filter it out. That's the common thing. And for this, sometimes we create indexes so that my filtering is faster, or sometimes we make a composite index so that it become, I want to search for a product name and some similar description, something, right? But we cannot have this type of index, the composite index, where two column, index together. But we can create index on the partial data, which we call the partial index. So while creating index itself, we have given the where clause where it filtering the data first and then creating the index, which is more faster. Or we can do a partition table where each partition is about product or the category or something, right? And then we create the index on top of that. So the first filtering is category or the first level, and then the second is the embedding. Now, storage considerations. PGVector can store 16K dimension vector. 16K is quite big. And 4 byte, as I said, 4 byte float. And we all know, I believe, the toast thing, right? The oversized attribute, right? This, by default, Postgres has 8 KB size. If it is not fitting in there, it has to be stored out of the space, out of the table, right? Out of the place. So PGVector, the vector data type is toasted data type. It will go out of the place. And by default, it is extended, right? And extended does what? It takes the 2 KB chunks by default and try to compress it, store it out of the place. And as we said, compression is not possible as such because it's a very random floating point number. So if we do try a compression where we're not going to anything, why to spend CPU on that? So with the new version, the PGVector supporting storing the PGVector data as an external, so the compression can be avoided, but still be storing in out of the table. And one more thing, the index can be created only with the 2,000 dimensions. It's pretty big though, but We have to remember we can store 16K dimension, but index would work only for the 2000 dimensions. So, little conclusion here. Whenever we are designing the system for PGVector or GenI or RAG thing, right, we have to think about the query and the query performance, which is very important in a sense. We need to retrieve faster data. At the same time, we have to maintain the accuracy of the data. Some experiment definitely would require, depending on the application we are working on or you are designing the system on that. Other thing that we need to think about is compute storage, because we would need to store the embedding in efficient manner, and efficiently we should be able to query them. PGVector is changing a lot. This area, whole GenI area is changing a lot. It's innovating. There are a lot of things happening. We really need to plan now so that we can adapt to new changes for tomorrow. Here is small demo. We have a video for that, but let me walk you through our test case. So what we are trying to do here, we are trying to generate SQL query using natural language, pure natural language. And assume if you give LLM to select 1,000 rows from some table, it can write it down. But each business unit, each company, or everybody has their own way of writing or naming the table structure, naming the column name differently. Sometimes it's totally opposite what it seems like to us, but sometimes it happens. Sometimes people, for generalization, keep the column name 1, 2, 3, 4, 5, right? LLM doesn't know about that. It knows generic things, which is very common. We, you, me, and all know about that. To mitigate that, we have a PG created a table, which is in Postgres a pgvector, which stores the metadata of the table structure where we want to query. So metadata is nothing but embedding, and the metadata means this table belongs to this schema, this table hold information about sales data, flight data, travel data, HR data, sale data, and the respective column detail as well, in form of embedding. When user fire a query or write a question to system, we convert the question to embedding. We send it for RAG. This is the RAG basically, when we try to retrieve. So the RAG first job is to retrieve the schema name, the query which user has asked us to write, on which schema it belongs to. Based on the question, it will try to find out in the metadata, which is embedding. It's a similar search, most likely it will find it out. And then it will find out what are the table involved in this question. It will pull out those information. Now, from VectorDB similar search, it will find out. And then it will add this context. This is the schema name, these are my table structure, and this is my question. Can you write this query? It would able to do it. Right? So there are two DB we are stating, but it's single vector DB. Only thing is we have to segregated the phases in which we are querying it.
I think before that we can just
Let me show you the demo here. I tried to make it a little faster. I hope it's a little faster. So what we are doing, this is the Jupyter notebook we have created, where we are importing certain Python module which is required to do it. And if you, this is, let me go back here. So if you see here, first line is okay. The second one is where we are creating the helper function to create the embedding. Whatever question user has entered, we are creating embedding for that. Give me a second, I'll just normal. I hope I can make it more. Yeah. So here we are creating the embedding, and then we're going to pass it on. Yeah. And this is one of the template of RAG, where we have defined a template for how we're going to query to LLM by passing the context, what we try to do, and what are the additional information we would need to do it. And when we get the response, and this is the, maybe you can go back, go to the bottom where we have ran the query, the end. I was trying to show you what are the questions we are asking, right? Here we are asking the questions, at the average course between, right? The question that we're talking, the example we were talking about it. This is the query, this is the question user has asked us. And we converted the embedding, and then we try to get the answer from LLM if we can write it down for us. Give me a second. Give me a second. So, yeah. So if you look at it here, first we are trying to find out the table name, schema name. This is the query we have written in Python. So it will try to retrieve, and you see we have given the parameter and embedding where we try to find out. It will give us the result back. And then similarly, we are trying to find out the metadata out there. And then we are generating prompt, where we have asked the questions here, how he need to do it. And then we are providing the schema name and username details. This is the prompt that we have. So it will call down, and it will show us the results. It's a quick demo, but I hope you were able to follow. Please, if you have questions, please raise. You can ask me. Yes, sir.
What happens if model changes after some time? Will it generate, the new model will generate the existing data, same embedding, same vector, or it will change? And if changes, then what happens to whatever I have in my indexes?
Yes, this is, thank you. Thank you for asking this. So the question is, first time when we use the embedding model, one of the embedding model we have used, now suppose the embedding model has been changed. So what would happen, right? In database, we have already generated the data for that embedding, and now the embedding, but remember one thing, the model that we have chosen, and the next model that we're trying to use, we have to choose with the same functionality. If it's changed, definitely result going to be changed. Or at least whatever changes happening, it support the existing or support the backward compatibility. Otherwise, it can mess up. It's not like that you have generated with Amazon, Titan, and later you use something totally different, which is not supported for the indexes that we have built, because they're going to be different. And there are standards. It's not like it's totally different, but definitely we have to understand that it should not be changed in that way.
So you have to use the same embedding, same model to generate your question embedding, and then the same model will be used to generate the RAG information. So that's how, and also whatever distance function that is used in creating that embedding model, the same distance function you need to use in your application to get the correct context.
Correct. So then I am basically tied up with the model, and after 1 year or 2 years, I found that model was not accurate.
And you have to regenerate your embeddings. So if you're changing your model, then you have to regenerate your embeddings, then you have to regenerate that data again and then store it.
I believe this area is still evolving, right?
Yes.
There would be some shortcut, there would be some support, which can be, have some compatibility.
So I have two questions. So is it possible to have one more column for the same data set and train that column with a different embedding model and then use either one of them? So similarly, like having 2-3 columns and then use trained on different models and then use whatever more relevance is met from out of those things. The second question which I have is this. I think there was some benchmarking which you are supposed to show, right? Like pgvector benchmarking. I didn't saw that, so I just curious to know what the scale looks like when we are, I mean, till up to what level we can use pgvector for all these use cases. So like when we go with millions of embeddings and more number of dimensions, so till up to what point pgvector can scale, and what are the scenarios where we have to go for a purpose-built vector database like Milvus or Pinecone or any other purpose-built vector databases?
Okay, so to your first question, whether you can store different model embeddings in your database, you can create 2 different columns with the vector type of it, and then according to the dimensionality that you are using in that model, you can have 2 columns, and then you can store that embedding into 2 different columns. And then, but while querying and while providing that, you have to use the same column and same distance function to make the application. So that is possible. On the second question, on the you asked about the what are the limitations on the PG vector, like on the benchmarking side. So in PG vector, you can store dimensionality till 16K. Beyond that, if your dimensionality is there, you cannot use the PG vector. And you can also index till 2000K. So if you 2000, so let's say if you have a 2K dimensionality, and then you have to create an index on top of that, that is possible. But beyond 2K, the index will not be possible.
For your first question, just want to add, because you're talking about adding one more column and having another data set created with different model, which could be efficient. But think about storing them together. It's going to, so you have to think about it, whether it's duplicate, because embedding is not small thing, right? Embedding going to take a lot of space. So you need to think and consider how you want to organize either. So definitely when you design system, you have to experiment with certain matrices with your application use cases to adjust them so that it gives you the right results. So
yeah, so it's a normal partitioning, like table partitioning that you have, you can partition the data based on the HNSW index as well. So normal, so it's a general, like we spoke about three general optimization technique like pre-filtering and then partitioning the data and also the partial index. So all these are applicable. Only the multi-column is not available with the HNSW, but rest all you can do to optimize your result.
his question was, can we partition the table and the differences? I believe the composite index, except the composite index thing, rest of the other thing you can do it, partition the table, and then you create the respective index on the partition wise. And the new thing is partial indexes that you can do it to pre-filter the data. Yes.
So let's say if you want to build your own model, so which is very resource intensive though, there are foundational model, various foundational model available. You can use that model and then further fine tune that model or add some additional training data to so that it caters to your application need and you can retune that model and use that. So instead of building, so these models are available.
Let me take that one. So first of all, we're bringing the data in VectorDB. So VectorDB is storing the embedding. There is no model at all. We are retrieving, we have a huge amount of metadata. We are querying for similarity, and that's the best place because massive amount of data, still we get the right performance with the vector search or similarity search, but there is no model at all. We are presenting the similarity based on the similarity results to LLM or the model to give us the data. If you train your model itself, who can do the things which you want it to be doing it, it's a different story, but think about it, cost, right? Training a model, and nowadays the generative AI is changing whole thing. If you train for a specific thing, it's very specific. And it requires a lot of compute power to train and everything, right? And you have to generate a lot of other things. It might work, might not work. But where LLM nowadays, if you give him the right context, right information, it can do the things which you want him to do it. And this is how we are using the VectorDB here.
So my model is not hosted with my data.
Uh, Thank you. Yeah, very interesting. I believe I had the same question some time back when I started, exploring this area. So, foundation model or LLM, they are totally different place. They are not in a database. They are hosted somewhere. They have a huge capacity, huge amount of compute power, which can answer you, right? Yeah. But to find out or give him the context, we are doing this thing so that it can answer it, rather than we create our own model and do it, right? So there are ways to, yes, so there are models, or you can bring your own, you can bring that model, import in your site, and you can do it your private network also. And there are offering where your data is not stored because it's in context, it's not stored. You have to think about which service you are choosing and which model, which offering that facility, or you can have it here, but think about it, hosting a model is very expensive.
I think we are running out of time. We can take further questions at our booth. So there is a booth outside. So we can take all the rest
take
of the
this, yeah.
questions. I believe
Go
we
ahead.
can take last one.
Yeah.
Yeah.
Hello? Yeah. You showed the demo where your program was answering queries based on company schema, right?
Right.
How did you do that? Like, did you train your own model for your own company data?
So that is where the RAG comes in. So basically, we are providing that RAG information. This is, let's say, my HR schema is there, my airline schema is there, and I'm providing that information. Okay, this HR schema has so many tables, and this is the meaning for that table. So let's say, if I employee table, all the employee data is there. So it gives you some context, and that context is again converted into embedding and stored in my embedding DB. So we are not using any modeling, or we are not remodeling it. That's the RAG information, which is the, I'm augmenting that data to my LLM so that it can answer into my context.
It's more like giving your documentation to, showing the documentation, respective
So
documentation.
you need to generate some embedding on that metadata as well.
Yes.
This is what we are doing, yes.
Got it.
So we are storing vector DB as a metadata so that when you ask the question, first we go to the documentation, look for the question that you have asked, find out the respective table or information or schema or nodes if you document, right? And then present to the LLM to interpret or give us what we want to do.
So does it work? Like, it generates a SQL based on
Yes,
the
it
structural
does.
language?
That's what we have shown, right?
Yes.
It is generating the SQL.
And it's fairly accurate.
Yeah. So it will be like based on the.
So I can get rid of my BI team.
Yeah. No.
But think about, you have to manage another DB which has to to maintain the vector DB, and how to generate the embedding, better embedding, so that you can utilize the new system that you are developing, right? It's not going to kill your job though.
So that's how all your generative AI application, it's generating text like normal. You put a question, it will get the answer.
We are right here, and if any more question, I'm happy to answer. And we are here in the AWS booth. Please come ask any question you want to do it. Thank you.
Thank you all.